Hello everyone, this is Brandon Burton with Restoration Sciences Academy, and I'd like to start off today by thanking you for joining us for this, the first in a series of webinars on restorative drying. Today we're going to focus specifically on one component of restorative drying, and that is on the importance of airflow. There are several different areas over the course of the next several months where we're going to bring webinars on some of the most critical components of restorative drying, and each of them will focus specifically on the ability to speed the rate at which we dry structures, to focus on the economy of drying structures and therefore the business cost and profitability of doing so, the ability to document and justify the process, etc. So each seminar will focus on the areas that are most specifically going to assist with your business needs. We're going to start off, as I said, with the importance of airflow because it's one of the more simple concepts and at the same time something that can very immediately be implemented into the business to directly impact drying rates. To start the topic, I'd like to talk just a moment about just how important air movement is from a number of different perspectives to restorative drying and water damage restoration. When you look at air movement is by far, the greatest majority of the equipment that is typically used in a drying process. It outnumbers a lot of the other types of gear and kit that we're going to use in a drying process, and it's for good reason that it does. And for the first part of the presentation today, I just want to pull out and highlight just how important air movement is to the process and the reason why that's a true statement. So again, thank you for joining us. I appreciate you spending the time with us this afternoon, and I look forward to being with you for a series of these webinars. You'll see information come out from Restoration Sciences Academy and from Dry-Ease UK that will give you some updates on when those subjects are going to be available and when we're going to host them. So to start the presentation off, first again, let's talk a little bit about air movement and why it's so important. And the best way to really highlight this is to not talk about drying, but to talk about something else very similar that we can all visually relate to very easily. When we're talking about drying, we're talking about taking water in a liquid or absorbed form and causing that water to change state, to evaporate or vaporize. Much the same as when you have ice and you're trying to get ice to change state and become a liquid. In this case, we're talking about melting when ice moves to a liquid, obviously, as opposed to evaporation. But the physics are pretty much the same. So I want to use this as an analogy for just a moment. In order to cause ice to melt, to cause that phase change to occur, there has to be energy that is applied directly to the surface of the ice. In other words, the energy that causes the ice to melt isn't the energy that's 3 inches away or 3 meters away. It's the energy that's directly in contact with the side of the ice cube. And once we begin the process of melting ice, immediately around the ice we see all the water that begins to collect. This water is cold because it just came from the ice, and it acts as a barrier that will slow down additional melting. And the only way to sustain the rate of melting is to find a way to remove the liquid, the cold liquid surrounding the ice, and immediately replace that with a much warmer body to continue or support the process. This is how air movement really becomes important, because air movement is the transportation mechanism that removes the effect of evaporation or melting in this particular analogy and constantly resupplies the surface with the right quality of air or water in this case in order to ensure that we continue to support the same rate. Now, with all that said, let me give you an analogy with melting ice that'll make some good sense. If we were to take an ice cube and drop that ice cube into a bucket of water, by dropping that ice cube into the bucket of liquid water, melting will occur over time. There are several things that are going to affect, however, how fast the ice cube melts. For example, if I take the ice cube and I drop the ice cube into a bucket of water that's at 20 degrees C, then the ice cube is obviously going to melt. But to speed the process of melting the ice, we don't have to make the water warmer. All we have to do is move the water, cause the water to flow, to circulate inside the bucket. Because as the ice begins to melt, even though the water was at 20 C, as the ice melts, the liquid melting off of the ice is going to be extremely cold right around the surface of the ice cube. It's going to form what we call a boundary layer. And now cold water is next to the ice, not warm water. So we have to cause flow inside the bucket. You take your hand, put it in the bucket, and start stirring the water around, and the ice cube is going to melt extremely much faster. It's actually something you can test just to prove out to in your mind just how important that flow is to continue that change of state. It's just take an ice cube from the ice chest next time that you're sitting around the freezer and throw that ice cube into a bowl or like a mixing bowl or something like that with some normal tap water. And just watch how fast the ice melts. It'll be a relatively fast rate of melting at first, but then it's going to slow down dramatically. Then begin stirring the water. And as you stir the water, start observing how rapidly the rate of melting begins to increase. It's a pretty dramatic impact. So that flow that we're causing in the bucket is the same thing that air movement is doing for us in the drying process. We're not trying to melt ice typically, although in some cases that's true. We're trying to evaporate liquid water, but the mechanics are exactly the same. In order to cause the melt or the evaporation not only to occur, but to continue to occur at that same rate, we have to constantly allow for a constant flow to the surface. So with that in mind, this is just an analogy here or an analysis of how quickly this ice will melt or how quickly water will evaporate with and without the flow. Now the flow has a name. The technical name for that flow is the transport mechanism in phase change, whether we're talking about melting or evaporation. Without transport, we can see here that we start with ice, this ice cube being 100% ice, and then over time, as time transpires, less of the ice is still ice and it's becoming liquid water. So how much of the ice is still remaining a solid is what we're looking at over time on the graph. If I provide no flow and no transport within the bucket, you can see that my melting rate is fast initially, but then it begins to slow down. And the reason it's slowing down is because we're forming that cooler water around the outside surface of the ice cube. Now if I add in flow into the process and constantly supply warm water to the surface of the ice cube, you can see what happens to my rate of phase change. Now in translation, this is my ability to dry a structure. Here in this case we may be looking at minutes, but in a drying process you can translate this to days, where without the appropriate flow within the drying environment, we may have some good drying initially, but that drying is going to rapidly slow down as we begin to form high humidities in and around materials, especially in cavities and in interstitial spaces or pockets or air voids within the structure. But if we supply the right amount of flow in and out of those spaces, my drying rate is going to be much more stable, and it's going to dramatically reduce the overall drying time. So with that in mind, when we do install air movement, the air movement has to have the ability to directly impact or contact the wet evaporating surface. And a good analogy for this is Newton's cradle. And I'm sure most of you are probably familiar with Newton's cradle, but in this analogy we have a series of balls that are all tied together from a bar up on the top side here. When this one ball rocks in motion and comes into contact with this edge of the series, the energy is directly transferred through these balls to the opposite side, and then this farthest moves away from the series of the chain. The only way that this movement is going to cause the reaction on the opposite side is if I've got contact. I have to have this ball contact this chain or series in order for that energy to transfer. So imagine this ball is the air movement. Air is moving through the space, it's moving through the structure, it's transporting with it the qualities that will cause drying to occur. If that air does not actually come into contact with the surface where the change needs to occur, then this movement is going to result in zero reaction. So not only is the flow important, but the flow must come into direct contact with the surfaces where the change needs to occur in order for it to instigate or facilitate that reaction. So here in an analogy, I've installed air movement within a space. You can see here by the blue arrow where I'm representing the flow. I could have a tremendous amount of airflow in the location where this arrow exists. But if the flow is this far off of my target surface, then it's going to have zero impact on my ability to dry the surface. Even if I get close and the air movement's within centimeters of the surface where I'm trying to cause the drying to occur, we're still not going to get the reaction from the flow. It must be immediately into contact with the target surface in order for the flow to have impact on the target surface. Now, in an open field like this, like a floor, it's easy to understand how we can achieve this. There are many different types of air movers that are available in our industry that will allow for this. Where it becomes more interesting and more challenging is when this wet surface is within these interstitial pockets and voids throughout the structure. That's when air movement becomes a little more challenging, and we have to get a little more creative with what we're using and how we're deploying it. Because again, if there's no flow on these surfaces that are hidden throughout the structure, then we're not going to cause that reaction to occur at that surface. Air movers have several factors in them that are important, several qualities to them that are important. Up at the top of this slide, we see a list of some of the more basic qualities that really have to be in a professional drying air mover. Obviously, they need to be able to operate safely in an environment over several days, if not a week or more on end. In order to allow occupancy in the space, or other contractors in the space, or even your own staff in the space while they're operating, especially in a damp environment. They need to generate a substantial amount of air in order to affect a good number of surfaces. That air volume also needs to be moving at a great speed. It's not just the amount of air generated by an air mover that's important, it's the speed of that air that's also important. At the same time, we're limited with the amount of power that we can run within the space, and even with the power that is available, it's also environmentally responsible for us to ensure that we're minimizing our footprint for power consumption as much as possible. And then last but not least, another standard quality of any air mover is that they need to also be able to generate this volume and velocity along the surfaces that we're actually trying to dry. And that's one of the big misnomers, and I'll talk about this in just a moment, about a number of different types of air movers, just generally speaking in terms of technology, that are out there. For example, your standard box fan and paddle fans type air movers, they can generate a good amount of volume. The challenge with this type of technology is that volume is not at all organized, and it does not have an ability to follow surfaces very well. Another component to air movement, however, has nothing to do with the air mover itself, and it's the user of the air mover. It's the installation of that air mover. There's a strategy to managing air movement, and the best way to explain the analogy behind that strategy is to use the wonderful rail system, the underground, and how that transportation system is strategically designed to ensure that we have all of the right capacity, all the right transport that is going to allow us to move people from one place to the other. And just like we're trying to move people with a rail system, the same is occurring with air movement in trying to move water or water vapor away from one surface and into an area where a dehumidifier or ventilation can handle that excess moisture and remove it from the space. If we don't have the right stops in the right places, if the train doesn't come into the right locations and then move to the appropriate location down the line, then the system becomes very inefficient, very ineffective. Same needs to occur with air movement. We have to ensure that we're using, first of all, the right vehicles, which would be the air mover types, and that we place those vehicles in the right places to transport the people or the water in the right locations. So understanding that, let's take a look at some of the different impacts that we get from different types of air movers here for just a moment. The first I'd like to take a look at are a series of images that are using a thermal imaging camera. And I'm sure many of you have used a thermal imaging camera, but basically, just in case you're not 100% familiar, a thermal imaging camera is going to give me the ability to see in false color a difference in temperature across the surface of a material using infrared light. So what we're seeing in this image is we are seeing a variety of temperatures across the surface. Where we're brighter in color here, more of a yellow color, the temperature is highest. And where we're darker in color here, kind of a purplish pink color, we are lowest in temperature. And the reason for the temperature difference in this image is because there is an air mover installed in the center of this floor, and this floor has been wetted, it's been misted with moisture And air movement, when it is actually moving across the surface of the material, is causing two things to occur. One thing that is occurring is where we're the deepest and darkest color, we're getting what we call evaporative cooling. That means drying is occurring at that location. Where we're bright white, not only has drying occurred, or bright yellow rather, not only has drying occurred, but we've completely removed all of the moisture, and now there is zero cooling, which has resulted in a much higher temperature. So the target here, when you look at this image to understand the impact of this air mover, is we want to see as much bright yellow as possible, and where we don't have bright yellow, the next best color would be a very deep dark pink or purple color. And where we have kind of this more bland color on the outlying edges is where we're not really making much impact at all. So you can see here through this thermal imaging, and I'll show you a couple of different air mover types, that not all air movers are built the same. In this particular air mover, we've got great impact out here in the middle, but almost like waves on a water when you throw a rock into the water, you can see the air kind of bounces over the middle here and then comes back down here over the edges because of the direct impact of that air movement blowing down on the floor. And that's what this is. It's an axial type air mover pointed directly down at the floor surface. When you move to a more common air mover in our industry, like the Sahara, you can see that its impact on air movement is very different. We have this area here, this zone out immediately in front of the air mover, where the air movement is extremely rapid, it's extremely high in rate, and where that highest rate is, we've made the most impact. And then we get a bit further out from the air mover, you can see we're still having an impact. There's still some drying that's occurring here, but the impact is not as substantial as where we had the higher velocity. Now, this image is important for helping us understand both the importance and the impact of an air mover. We learned several things from this. One, our drying rate is always going to be fastest where the air movement is moving the fastest, and that's where we have the greatest speed, is closest to the air mover. It's also going to only be impactful when the air is in direct contact with the surface. As we saw from the first image here, where we had direct impact from airflow, we had great ability to dry, but as we lost some of that impact, as the air literally began to bounce back up off the floor, we lost the influence of some of that airflow. Those are two very, very critical, very important lessons for us to know and understand. Just to further drive that home, I'll show you a third image here. Here is a specialized air mover that uses technology to keep the air down in contact with the surface. There's a special grill on the bottom side of it. And you can see, using the same type of axial as we saw in the first image, how we have much more even coverage across this floor in drying. The reason for this is, again, we're keeping the air out in contact with the floor for a longer period of time. And the lesson learned here is just how important it is in a drying process to ensure that we do get that blanket of air movement across all of the target wet surfaces. Moving away from these images, I want to move into specifically into the Sahara type or carpet dryer type air mover here for just a moment and do some similar thermal imaging analysis. This is using a slightly more recent thermal imaging camera. It's got a much more impressive color scale on it, but in reality we're looking at the same thing. Up at the top of the screen here is the outlet of an air mover. Moving down from that air mover across the wet carpeted surface. Where we have bright white, we've had the most drying. Where we have reds, we have good drying. Where we move from yellow into blue, there's some drying occurring. And out here in the green, there really isn't much happening at all. So I want to see lots and lots of whites and reds as I take a look at these images. These are just a couple of different air movers of that same technology, and just showing the fact that there are differences in one design to the next, where the air mover has the ability to generate more flow down in contact with the surface. What you're looking at here in the center, by the way, is the Sahara air mover as compared to some of the competitive models that are out there. On the far side over here, an air mover that I'll actually mention at the very end of the presentation that I know Dry-Ease is just now bringing out into the market to make available. I'll talk a little bit about that at the very end. But with all of that said, regardless of model or type, again, we learn the same lesson here. It's extremely critical to ensure that we're maximizing the contact of air with the wet surfaces where drying needs to occur. And anywhere that the air movement doesn't exist, and that weakness existing with all of the images that we've seen, anywhere there is not airflow, we're not going to have the drying performance. An analogy to this would be that, if I can dry 30 or 40 or 50% of the structure in a week, and this remaining 60-70% of the structure takes me 4 weeks, then the job didn't take a week, the job took 4 weeks. And that's probably one of the most important things to stress about the importance of airflow, is it doesn't matter how quickly we dry some if the majority takes us substantially longer. It's the longest point in terms of drying that's going to dictate how long the drying project took. So with that in mind, let's go ahead and move into some specific mechanics for air movement now. I want to show you an analogy here, or an example of how to manage this installation of air movement to maximize flow across surfaces using a really simple structural diagram as an example. Here we see the diagram just as a literal sketch diagram. We've got a larger room and 2 smaller rooms that are offset from that, a couple of doorways. Here we're just taking a look at that in a 3D perspective view, same room. So this is the larger room in this area, and we've got a couple of smaller rooms here that are open from doorways. Let's imagine for a moment that all 3 of these are actually affected, all 3 of these rooms. And I'm trying to ensure that, especially on these floor surfaces where the water predominantly exists, that I'm getting good universal airflow and coverage. So with that, let's take a look at how we would use some different types of air movement. First of all, we're trying to ensure that 2 things happen in this space as it relates to air movement and the transport mechanism as we refer to it. First of all, I need to ensure that the temperature and the humidity in all 3 of these rooms is the same. If I put a dehumidifier in one of these rooms, a large capacity dehumidifier or a medium capacity dehumidifier, these are relatively small rooms. They don't necessarily need a dehumidifier in each. That would be a very inefficient use of power and resources. So in reality, 1 dehumidifier would probably be appropriate to handle the load. The challenge is, if I put the dehumidifier in just this larger room, then I'll probably end up with a warmer and drier air mass in this room and be cooler and wetter in the surrounding rooms, which means this main room would dry much faster and these neighboring rooms would dry much slower, which obviously is not going to be efficient. The best way to manage that process and ensure that I have a good, even, balanced temperature and humidity throughout is to use the actual wall assemblies as my ducting, if you will, or as my ability to transport the air between rooms. So I want you to just follow this dot as it moves its way around the room, and notice that if I follow the wall assemblies, I'll end up walking into and out of each one of these rooms as I walk through the wall, along these wall assemblies. That's going to be managed appropriately if I use a centrifugal air mover. A centrifugal air mover has a very unique trait in that it has an outlet in the front and an intake on the side. And that intake immediately on the side is only on this right-hand side of the air mover. The left-hand side of this air mover is not an intake. It is an area where we've got a power switch, we've got some information printed on the side. It's where my power cord comes into the air mover. It's also where the butt end of the motor is. This is not the intake side of the air mover. The intake is on the opposing side. So if you take a look at that intake being on that side of the air mover, notice how it's going to draw the air out of one room and force it down the wall of the next. Again, with that same orientation, drawing it out of the main room and force it around the walls of the next, and again pulling it out of this room. This is going to cause an air exchange to occur between all 3 of these spaces. These 4 air movers are by far going to be the most critical air movers that would be installed in this space when all 3 rooms are affected. It's the same as having a heating system in a commercial building, or in some cases even a residential building, where you have a centrally located heater or air conditioner that is in one space. Maybe it's in a utility closet or something similar, and in that one space it is effectively heating or cooling the entire structure. We don't have a furnace necessarily in every room in a system like that. What we use to deliver the heating or cooling throughout the entire building is ducting, what we call supplies and returns. The ducting pulls air out of rooms, brings it to the heating system, and then brings the heated or cooled air back to those same rooms. And that's essentially what these air movers are doing for us. They're using the wall assembly, the footprint or the layout of the rooms, as a ducting system to evenly distribute air throughout the space or throughout the property. So with that in mind, that covers the perimeter of the area quite well. But what is still lacking or missing air movement is the center of the rooms. And this is where the axial type air mover that we looked at earlier becomes extremely beneficial. We looked at those thermal imagings. We looked at an air mover pointed straight down in the middle to create airflow out in the middle of the room. The axial air movers that are designed for this will typically have a standoff or legs that allow the outlet of the air mover to remain, enough space above the floor to allow the air to move out of the air mover and then down across the surface of the floor. And that'll address that surface area that we have out in the middle to ensure that we have a good, even, consistent amount of airflow across all of our target surfaces where we're trying to cause drying to occur. Now, to verify this, there are several things that you can do. Probably the most scientific or the most effective way, once you've had air movers installed this way to verify that you've got everything covered, is to grab a thermal hygrometer and take your temperature and your humidity reading as you walk through the space, and take that reading up here in the middle of the room, the air in the center area, and find out what your temperature and humidity is about halfway between the floor and the ceiling. Once you have that temperature and humidity reading, then move the thermal hygrometer down to the floor surface. And everywhere where we've installed this airflow, we should find the same temperature and humidity on the wet surface that we're finding up in the middle of the room. If there's a deviation between the temperature and humidity in the middle of the room and on the floor, there's not enough airflow. It does not matter what the temperature and humidity is in the middle of the room. If the temperature and humidity on the surface of that carpet or that wall or whatever the material is higher in humidity or lower in temperature, then it's going to dry slower than it should be drying. The air movement is not properly delivering the air to those surfaces. And to further emphasize that, it's not just this room or this target area where that temperature and humidity is so extremely important. It's also in these neighboring rooms. If you remember, we had two subsequent areas over here and immediately adjacent to this room where the temperature, the humidity, etc., again, was just as important. So the air movers that we looked at earlier for installation would also need to be installed in those same areas to ensure that we were pulling moisture, temperature, and humidity out of these rooms, delivering it into the next room, moving that temperature and humidity throughout the space, again delivering it to this adjacent room, then pulling it out of this space, and using this entire wall assembly to bring that same circulation of air back to its point of origination. And when we generate that type of circulation, then it does not matter where the dehumidifier is installed. And instead of using smaller, multiple, less efficient dehumidifiers, we can centralize and use one larger, more efficient dehumidifier. Not necessarily larger, but just higher capacity, especially with some of the new low humidity dehumidifiers that we have available. A single one of those machines, which draws a third of the power of using smaller, less efficient machines, is very efficiently going to handle the humidity control throughout this entire space, as long as this air mover or air movement has been installed appropriately. Then once this perimeter flow has been set in this direction, the last piece here that we discussed is ensuring that we do the same thing by covering the center of the floor out here in the middle of the room. Again, axial air movement to generate airflow from the center out is the best way to achieve this, especially when the reason why we're having a challenge with air movement out here in the center of the room isn't just because it's a large open area, but maybe out here in the middle we've got lots of contents. So we've got lots of sofas, bookcases, chairs, etc. that were along the perimeter of these walls. In order to generate the airflow, we had to move these out away from the perimeter of those walls. Typically that means they end up getting collected out here in the center of the room. So a best way to manage that would be to install one of these axial air movers in the center, as we just discussed, pointed directly down, then bring the contents out towards the center and basically circle those contents around the air mover. When we do that, we generate airflow not only across the surface of the carpet or the floor or the rug, but we also get airflow along the bottom of those contents and ensure that we're drying the fabric and the wood, etc., or the textiles of the furniture or contents that have been relocated within the space. So as a summary, it's critical that we generate air movement across every one of the target wet materials that we're trying to dry within the space. That is best installed or assured by ensuring that we strategically place air movement to ensure that we're moving or transporting air throughout the entire drying space. As we install those air movers, it's critical to ensure the air movers are working together in series, as we looked at in this previous slide, where one air mover is working with the air movers before it to draw air completely and thoroughly throughout the entire space. Usually this is best done by starting with wall assemblies and using your centrifugal type air movers or similar to draw air from those rooms one to the next. Once that's installed, then we need to verify that we also have good, even airflow coverage throughout the field of every space or room. That's generally best done by using an axial type air mover. So we can generate that flow across the center of those rooms, especially when we have contents within the space. As we talked about just a moment ago, if we do have things like sofas and furniture, etc., out here in the middle of the room, this is where they would be physically located during the drying process. So the air mover out in the middle can address the base of those contents while we're addressing the balance of the room. Then the only thing that's left and remaining once this air movement strategy is deployed is if we do have moisture inside of walls or underneath cabinetry, etc., then we need to move to yet another category of air movement to ensure that we're getting airflow within those spaces. Either the base of the cabinets need to be opened so that the airflow from this air mover can move beneath those cabinets, or we need to use our specialty systems that force air or inject air within those spaces so that we can ensure again that our transportation system is addressing or affecting every one of those spaces where moisture and drying exist and need to occur. So that's the general strategy on air movement. Notice here, by the way, as just a general principle for installation, that all of the air movement in every one of these rooms was in a clockwise orientation in these rooms. If you're using this particular air mover, that clockwise orientation is critical because, again, the intake for the air mover is on this left-hand side only. That, on this analogy, would be on this side of the air mover. This side of the air mover is not an intake. So if I went in the opposite direction with my air movement and went this direction around the room, I would not have an intake drawing from the neighboring room. It would be the motor assembly that would be presented with the airflow, not the intake of the air mover. So clockwise, if you're using that centrifugal type, a Sahara type air mover, is critical for that orientation. Counterclockwise rather, simply will not work. Having said that, one of the last things I want to talk about today, moving into a quick discussion on some newer technology on air movement. There are technologies where clockwise and counterclockwise really doesn't matter. And some of you may have had an opportunity to be exposed to the new type of centrifugal air mover that's out there, something that's made by Dry's, the Velo. But that intake that we were just talking about, just in case this is something that you're playing with or you've already got an opportunity to use in your fleet, the intake on that air mover is here. So in this particular air mover type, when I operate it in this orientation, again, it would be a clockwise orientation of airflow. Intake on the left-hand side, outlet in the front. But this can very easily be flipped over, and the intake can be on the opposite side. So if you're using an air mover like this, you can go in either one of those directions. What's important, however, as a project manager, as a restoration contractor, is just ensure that whichever air mover type that you're using, we've got to have a universal movement of air throughout the space where each air mover is working with the other air movers within the space. No two air movers should be working against one another. That creates a lot of turbulence. It absorbs or deflates a lot of the energy that air movement should be generating across the target surfaces where we're trying to dry. So they should all be working together in series with one another. Now, the last thing I want to show you here before we begin to wrap up, and as I do this, I'll just make a quick note. There is a chat area in the up on the menu bar. There should be a small bar that you see that has a little telephone icon, then a speech icon, etc. That little chat icon that's up there, if you have a question that you want to make sure that I address before we wrap up today, please do me a favor and make sure that you throw that question into the chat area. If I see a question in there when I wrap up, I'll make sure that we do our best to address that. So with that in mind, one last thing that I want to show you, I want to roll back up to the thermal imaging here real briefly. And on the thermal imaging, That last air mover we were just taking a look at, I'll just throw a little plug in for that new technology. This first slide that we saw was generally what we'll call an inferior carpet dryer. And a carpet dryer that really hasn't been designed with the ability to cover surfaces very well. In the center here we have what we would call the more professional grade, the Sahara type centrifugal air mover, and we can notice here what happens to the amount of coverage that we get from an air mover like this that's had that type of engineering put into it. This last image over here is that new Velo air mover. And notice here what happens to the amount of surface area that we're covering with that particular type of air mover. We're increasing, even over something like a Sahara, we're increasing the coverage somewhere in the neighborhood of about 20 to 30%. And we're doing that with about half the power consumption. And the way that that's done is it's done by really specifically engineering the air mover's outlet so that we ensure that all of the air generated by the air mover is placed into direct contact with the floor. And you'll notice that when you take a look at this image that the snout or the outlet of this air mover has a downward slope to it, and the side of the air mover has an inward slope to it. These two effects, they're what we call stabilizers, a horizontal and a vertical stabilizer. And what they do is they ensure that all of the air generated on the inside of this air mover, if you'll notice by the shape here, is being harnessed and directed into direct contact with the flooring surface, which means more of the air ends up generating work in the drying effort. It's just a little more smart on the technology. It's a little better intelligence in what we call fluid dynamics and managing the way the air flows out of that air mover. And by doing this, we can use less power, we can use less space. This air mover is about half the size of a Sahara height-wise. You can fit more of them on the vehicle and still get more work done with them at the same time. So didn't want to turn this into a product presentation, so don't want to spend any more time on that. But there were a couple of different questions that did come in. One of the questions that I did see come in a number of times, it looked like a couple of you did have some technical glitches in getting into the audio. And with that, I did record the presentation today, so all of the information that we covered today is going to end up being posted for content, for reviewing the content afterwards. So anybody who had that issue, I will make sure we get that addressed for you. So, so with that in mind, that was really the only question I saw come up. So I'm hoping that that meant that the information went across well. The presentation itself is something that definitely can be used for delivery by yourself for the rest of your organization as well. I would encourage you to use the recorded version as much as possible, but if you feel there's some content within it that you'd like to pull out and use for technical training within your organization, that's the reason why Restoration Sciences Academy is here. In fact, I'll give an early announcement to something that we're going to release a bit later down the road, and that is that we're in the process of actually developing some training tools that you'll be able to use in your organization for exactly this type of technical content for internal training. Kind of the long-term plan here with Restoration Sciences Academy is that we'll do a lot of this type of activity to bring you technical training and content in a format that you'll be able to use and implement within your organizations for internal training purposes. So you'll see a lot more of that from us coming down the road. So with that, folks, that's about 40 minutes here on the presentation. It's about what I had targeted. I want to thank you very much for joining us today. You will see a schedule that will come out, and that schedule that comes out will highlight a number of different series that are much like this, that'll each focus on a specific area to help us dramatically improve our ability to dry structures, in many cases utilizing many of the resources that you have already in your arsenal, and in some cases also encouraging you to think about some of the newer, better technology that's out there today. So with that in mind, I appreciate your time, and any product questions, by the way, I did see a product question come in on the Velo. Any product questions on the equipment, I'll direct you straight over to Dry-Ease Limited on that, so Dry-Ease UK. So get a hold of Colin or Paul or Ann or somebody over there at Dry-Ease, and they'll be able to get you the specs on it. So thank you very much, folks. I appreciate your time, and we'll get an email out to the group here once the recorded version of the presentation is ready for you to review. So thank you for joining us. I look forward to having you with us on the next presentation approximately 1 month from today. Thanks for your time.